Hi everyone! In this video we are going to go over leaving groups, which is the last topic that really affects SN1 versus SN2 reactions. So remember, in an SN1 reaction, the first step is the leaving group leaves, and that's the rate determining step. So leaving groups are really important for SN1 reactions, because the rate determining step depends on how quickly that leaving group can leave. So let's write that leaving groups are very important in SN1 reactions. And that's because they are involved in the rate determining step. Now, what about SN2 reactions? Remember that everything happens in one step, so the nucleophile attacks and the leaving group leaves. So leaving groups are still somewhat important in SN2 reactions, so we'll just write that leaving groups are moderately important or somewhat important in SN2 reactions. And that's because the leaving group and the nucleophile are involved in the rate determining step. And I'm just abbreviating that as RDS. Okay, so let's compare two alkyl halides and their leaving groups. So on the left, we have an alkyl halide with iodine, and on the right, we have an alkyl halide with bromine. So which of those halogens is the better leaving group? So one way that you could think about this is, when the leaving group leaves, how stable is it? And remember that in this case, when iodine leaves, it's going to take those shared electrons with it. So it's going to become negatively charged. Same with bromine. Bromine's going to take those electrons that it shares with it. So it's going to become negatively charged. So really, we're comparing the stability of I- and Br-. So which of those two leaving groups can hold a negative charge better? Which one is more stable? Now, another thing to think about is atomic size. The larger an atom is, the more able it is to accommodate extra electrons. So larger atoms can accommodate negative charges better. And we say that they're more polarizable, so they can kind of spread out that negative charge better. So is iodine larger or is bromine larger? Iodine, right? It's further down the column, and atomic size increases down a column. So iodine is the more stable leaving group. So we'll write that this is the better leaving group because it is more stable due to its larger size. All right, so this is actually really similar to a long time ago when we were comparing the stability of conjugate bases. So back then we were using cardio rules, and you can do the same thing here. you can kind of step through, okay, what's the charge? Well, we have a negative charge on both of these atoms. And then the next letter is A for atom. So then we compare the atoms. And in this case, they're both in the same column. So we want to compare them based on their atomic radius. And iodine was the larger atom, so it accommodates the negative charge better. Let's look at another example. Let's say we have the following molecules. One has, oops, didn't mean to draw a double bond there. One has an ester group, and one has an ether group. So I'll just circle the leaving groups. And remember, you can step through cardio to figure out which one is more stable. So I'd like you to try this one on your own and see if you can figure out which leaving group is more stable and is therefore the better leaving group. And you can pause the video if you would like. All right, so we'll do what we did last time. We'll just show what the leaving group looks like once it actually leaves. So in the example on the left, we would end up with a negatively charged oxygen. And on the right, we have a similar negatively charged oxygen. So if we step through cardio to compare these two leaving groups, the charge is the same on both. The charge is on the same atom, which is oxygen for both. So let's look and see if there's any resonance for these leaving groups. Yes, on the left-hand side, we do have a resonance structure. So we could move electrons around to form a second resonance structure. The molecule on the right, however, or the ion on the right, does not have a resonance structure. So that tells me that the leaving group on the left-hand side, the ester group, that is more stable due to resonance. So that means it's the better leaving group. So again, the leaving group stability is directly related to conjugate base stability. So we can just follow those cardio rules when we're trying to determine which leaving group is more stable. Now, luckily, there is a super handy table showing the stabilities of different leaving groups. And I recommend making some flashcards on these groups. So maybe on one flashcard, you could put excellent leaving groups on one side, and then on the other side, just list the excellent leaving groups. And then on a different flashcard, you could put poor leaving groups and kind of quiz yourself on what poor leaving groups look like. So for instance, excellent leaving groups are the halides or negatively charged halogens, except for fluorine. Fluorine is our exception. So notice over here, fluorine, or fluoride, I should say, it's typically an extremely poor leaving group because it does form really strong bonds. So it does not leave very easily. But the other halogens are good leaving groups. The conjugate base of sulfuric acid is a good leaving group. And then we have something called tosic acid. And its conjugate base is actually a really good leaving group because it has a lot of resonance. So it's very stable. And then last but not least is water. Water is a really good leaving group. Now, there are some moderate leaving groups, so groups that, they can leave, but they might not be super stable. So these would be, for instance, the conjugate base of a carboxylic acid. We also call that a carboxylate ion. And we'll learn more about those later on. And then ammonia is also a fairly good leaving group. Now, when we start going down further, we get into the poor leaving groups. And these groups are poor leaving groups because they're strong or very strong bases. So for instance, the hydroxide ion is a poor leaving group. Alcohols are poor leaving groups. Or I should say the conjugate base of an alcohol is a poor leaving group. The conjugate bases of amines are poor leaving groups. If hydrogen has a negative charge, that's a really bad leaving group. It would prefer to be neutral. It doesn't want to have a negative charge. And alkanes with negative charges are also really bad leaving groups. Now, there is one way, or actually there's a few ways that you can convert a poor leaving group into a better leaving group. So let's look at those different methods. So for example, let's say that we have an alcohol, but we want to convert that into an alkyl halide. So we want to replace that OH group with an I, or an iodine. So one way that we could potentially do this is we could react our alcohol with an iodide ion. And the sodium ion here is just acting as a spectator ion. It's just balancing the charge. So we would expect that that iodide would attack the carbon next to the OH group, and then the OH group would leave. And we end up with our alkyl halide as well as sodium hydroxide. However, remember that OH is a bad leaving group. It's a poor leaving group. So what we want to do is convert that into a better leaving group because this reaction would not happen. OH would not leave on its own. So we need to convert OH minus into a better leaving group. And there are a few ways to do this. So the first way is to protonate the leaving group. Oh, proton. Let's see, protonate the leaving group. So instead of using sodium iodide, what if we use the acidic version of iodine, so hydroiodic acid? Well, in this case, what's great is the OH group is going to act as a base, and it's going to take that proton, and then we'll leave electrons behind on iodine. So we have a proton transfer. And this converts OH into a better leaving group, which is water. So remember on the last slide, we said that water was an excellent leaving group. Let's see, and then we also have I minus, and now that iodide can act as a nucleophile and attack the carbon next to the leaving group, and then the leaving group will leave. So now we get our alkyl halide that we wanted to form, and our other product is water. So some pros for this type of reaction: we have a high atom economy. So most of the atoms end up in the products. However, the cons, there could be some side reactions. We might have some acid-base chemistry going on off to the side, so we might end up with some weird products. So we could have contamination in our final product. So acid, oops. So we'll just write that one of the cons is acid-base chemistry could occur. So we might not get the product we want. Now, there is a second way that we could convert OH into a better leaving group, and that involves converting OH into what's called a tosyl group. So remember that tosyl acid we saw on the chart? This is that group. So let's say we have the same alcohol that we had before. We're going to react that with something called tosyl chloride. And we have a methyl group off to the end there. And I drew an R up above, but that is just the alkyl group off to the side. And that's just a way to abbreviate the that group, since it is quite large. So this is our tosyl chloride. And we can abbreviate that as TSCl. Now, when we use tosyl chloride, we do have to also add pyridine, which looks like this. It's kind of like a benzene ring, but one of the carbons is a nitrogen. And pyridine is just a weak base that helps the reaction occur, but it doesn't actually react with anything. So it's just there hanging out, and it does help the reaction. But the two go hand in hand. You have to have pyridine in order for this reaction to work. So what we end up with is the following. See if I can squeeze that in there. So basically, the oxygen and the sulfur form a bond, and then the hydrogen and the chlorine form a bond and form HCl. So we've got our new bond and our other new bond. Now, the next thing that happens is the, we then add the iodine, or the iodide. Oops. And the iodide then can come in and attack the carbon next to our leaving group. the leaving group will leave, so that oxygen will take these shared electrons with it. And we get our alkyl halide that we wanted. And we also get another product, which is the ion of the tosyl group. And I'm just going to write R for the benzene ring with the methyl group attached. And you'll also notice that because the oxygen on the end is negatively charged, we have multiple resonance structures. So this is a super stable conjugate base. So the negative charge could move in to form a pi bond, and then we could move one of the other pi bonds to an oxygen, or we could even have the other pi bond move. So there's 3 different resonance structures there. So this is a very stable leaving group due to resonance. All right, so some pros of this reaction: you're avoiding any unwanted acid-base chemistry. But some cons: there's very low atom economy. So that tosyl group is quite large, and it doesn't end up in the product that we want. So we have all these atoms that are kind of useless in a way. So the atom economy is really low. But this is a good alternative to the first method if you are experiencing some weird acid-base chemistry. Okay, so let's finish up that nucleophilic overview chart that we've been filling out. So remember, previously we had gone over the mechanism for both SN2 and SN1. We said that SN2 happens in one step. SN1 is a stepwise reaction, so the leaving group leaves first, and then the nucleophile attacks. We then derived the rate laws for both. So we said that SN2 is dependent on, or the rate for SN2 is dependent on both the substrate and the nucleophile. But for SN1, the rate is only dependent on the substrate. And then for stereochemistry, we said that SN2 produces only the inversion product, whereas for SN1, both the retention and inversion products will form, but there is a slight preference for the inversion product. And then we went over the role of the electrophile, and we said that the electrophile should be quite small for SN2. So we should have either a methyl group, a primary carbon, etc. And then once you start getting into the bulkier groups, that's when SN2 doesn't really work anymore. However, for SN1, it's the opposite. So if you can have a tertiary carbocation as your intermediate or a secondary carbocation, that's pretty good. We want that carbocation stability for the intermediate. And then we went over the role of the nucleophile, and we said it's better if the nucleophile is less bulky and unstable for SN2. But for SN1, it doesn't really matter what the nucleophile looks like because it's not part of the rate determining step. So now let's talk about the leaving group. So we just said that for SN2, the leaving group is moderately important because the nucleophile matters as well in the rate determining step. And for SN1, the leaving group is very important because it is the only thing involved in the rate determining step. And then before that, we had talked about the solvent, right? And we said that polar aprotic solvents are better for SN2 reactions because there are no hydrogen bonds. But for SN1, polar protic solvents are better because they help stabilize the leaving group. Once it leaves. So we'll put a negative charge on the leaving group to indicate that it's already left. All right, so hopefully this chart helps a little bit when you're thinking about SN2 versus SN1. And let's actually go over a practice problem before we end the lecture. All right, so let's say that we have the following. So we have an OH group on a butane chain, and it's in a wedge position. But let's say that we want to convert that into a thiol group, so a sulfur attached to a hydrogen. How would we do that? So the first thing we should think about is our nucleophile would likely be SH minus, right? Because we want that to come in and attack the carbon next to the leaving group. Okay, so we want SH minus as our nucleophile. But then notice that the product is inverted from the original reactant. So we have an inversion product. So do we have an SN1 or an SN2 reaction? SN2, right? Because remember, SN1 would produce both the inversion and the retention product. Okay, so we know that the nucleophile is going to attack first, and then the leaving group will leave at the same time. But we also have a terrible leaving group here. So we need to convert that into a better leaving group. So how can we do that? And actually, I'm going to erase our nucleophile since that's going to happen in a different step. So in the first step, we want to convert OH into a better leaving group. So we'll have some sort of intermediate here. And then in the second step, we want to convert that intermediate into our final product. So see if you can figure out a good way to perform this reaction. And you can pause the video if you want to try this on your own first. Okay, so let's try using the Tussle chloride method. And we'll convert that OH group into a Tussle group. So we'll just abbreviate that as OTS to make it easier. And then we want to turn that OTS group into a thiol group, or SH. So let's use sodium bonded to our thiol group. And because this is an SN2 reaction, What type of solvent should we use? Should we use a polar protic solvent or a polar aprotic solvent? Polar aprotic. So maybe we would use something like acetone. And acetone dissolves a lot of things, so that should work. So again, polar aprotic solvents favor SN2 reactions. And down here we have acetone. All right, and then we know from previous discussions that in an SN2 reaction, we end up with only the inversion product. So this is actually a synthesis problem, and this is something we're going to do a lot of next quarter. We'll start doing a little bit of synthesis here at the end of this quarter, but next quarter we're going to really start thinking about how we can go from a reactant to a product. What reagents do we need? What kind of products might we end up with? Are there any side reactions that could occur? So there's a lot to think about in these synthesis problems. All right, so I think we'll end there. And you probably have all the information you need in order to work on the homework assignment where you try to figure out whether a reaction is SN1 or SN2. So that homework assignment is the substitution activity assignment. And if you do have any questions, just let me know. But I'm also going to post a video kind of going over a couple of those problems so you can get started. But definitely use this table as a guide. This will help you figure out if you have an SN1 reaction or an SN2 reaction. All right, so I will see you in the next video.